Hello my dear, welcome to IMS GATE Academy. I hope you are all good. I am Pragyabrat Tripathi, Faculty Department of Mechanical Engineering. So my dear, we'll continue with the thermodynamics lecture, and in this we already completed that example of reversible cycle. That means what is the Carnot cycle, and why this is important beta, that means if you model any cycle, for the maximum output or a minimum input, I repeat, if you design any cycle for the maximum output or minimum input, you can always thought on the Carnot cycle. That means the Carnot cycle is a model in which the work output is maximum and work input is minimum. That means if you design any work input device, so what is your motivation? Motivation is that you want always put the minimum effort to it, okay? So accordingly we design the Carnot cycle, okay, no problem at all. So we done all this cycle, all the process, that means adiabatic compression. What is the adiabatic compression? How to achieve? That means we start point 1, 2, 3 and 4. That means 1 to 2, 2 to 3, 3 to 4 and 4 to 1, right? What is mean by the adiabatic compression? That means the fluid will compress from compress from point 1 to 2 during the adiabatic. That means it is very less chance. That means we can neglect the heat transfer through it. That means we design a wall that is a resistance the thermal stresses. That means it can never allow the heat transfer from the system to the surrounding and surrounding to the system. Then you compress it. Automatically when there is an adiabatic wall, that means you cannot transfer the heat. So you apply the first law of thermodynamics, dq, del q is equal to du plus del w. So in that case, their heat transfer is 0 and work you giving negative. That means work input is negative. So its internal energy will increase. That means pressure increase, pressure increase, volume decrease and internal energy will increase. So if we draw the graph on a PV diagram, so my dear, this is a pressure and specific volume diagram. So there is a 1 to 2 is adiabatic compression. 1 to 2 is a adiabatic compression. So 1 to 2 is the adiabatic compression, okay? So this is the compression. Now, again, if when you compressed, now you allow the expanding of the gas. That means if you compress it, its internal energy will increase. That internal energy increase will increase the temperature, and now you want to, now there is an expansion. That means there is a compression and then you supply a heat to it. That means during the compression you supply a heat to it, okay? So if once you supply the heat, and that heat will supply to a reversible manner, total reversible. Mind it, the Carnot cycle is the total reversible cycle. That means it is internally also reversible or externally also reversible. How to make the cycle is internally reversible? Due to the quasi-static process. That means you can neglect the dissipation effect. That means if you move the piston very slow manner, during that we can neglect the dissipation effect. That is the internally reversible. And now how to achieve the external reversible? The external reversible will achieve due to the infinitely small temperature difference. So the temperature difference between the source and the boundary of the system is very minimum. That means delta T tends to 0. Okay? Now again, so there is an isothermal expansion. That means you can expand. This is your compression, yes or not? This is your compression, adiabatic compression. Now isothermal expansion. If you expand the gas, that means this is isothermal. How to achieve the isothermal? See, if we supply a heat to the system, system temperature will increase. If the system temperature will increase, so how can you achieve the temperature remains constant? You expand the piston. That means heat supply, temperature increase. You don't want to increase the temperature, expand the piston. Accordingly, there is a expansion. That means that expansion is throughout the constant temperature. So this is your expansion, no problem at all. This is your expansion. Now again there is a expansion. So expansion, now you put the insulation. This is the insulation. This is your insulation. This is your insulation. This is your insulation. Put the insulation and allow the gas to expand. That is a power stroke. In this situation, there is a power. That means you can expand the gas with no effort. Here is the compression. Here is the expansion. Due to the effort, heat supply you can, but in this condition you cannot supply a heat. So during that expansion, work will out. This is called power stroke. So again there is a expansion, but again there is a expansion is adiabatic. So there is a two process adiabatic and two process isothermal. Two process isothermal. Isothermal expansion, isothermal compression. Adiabatic expansion, compression, adiabatic expansion. So again there is a expansion. Again there is a expansion. Again there is a expansion. So this is expansion. Again there is expansion. Now again there is expansion. So it is expansion. Now what we want? There is expansion. Now you reject the heat. That means after the expansion, you can achieve the initial position, you reject the heat so that the piston will reach the initial system. So there is a compression. So isothermal compression, volume will increase, volume will decrease, pressure will increase. So this is your isothermal compression. So this is your cycle. This is point number 1. This is 1. This is 2. This is 3. And this is 4. Okay. So this is 4. Okay. This is 4. And the why we yesterday? Yes, very good question. See, it is not a practical cycle. Yes. See, the answer of this question have a many different way. The simple way is that this is the hypothetical cycle, so you can achieve the maximum efficiency. You can achieve the maximum efficiency, number first. Now you can design a cycle for that given temperature range. What you design this, that means what is that design? This is your TH and this is your TL. Okay, so you can design accordingly this cycle. You design the same temperature limit of the cycle and find the efficiency, and that efficiency you compare. Okay, now let's suppose if you find the efficiency of this Carnot cycle, it is 70%. Okay, now if you design a cycle, practical cycle with the same temperature limit, and your output temperature is, let's suppose, 40%. So there may be a chance at a given temperature you can achieve the temperature efficiency as possible as maximum. Why? Because you already at the same temperature limit, your efficiency maximum is 60%. So there is a freedom, so there is a possibility to achieve how much the maximum efficiency. Due to that reason, the Carnot cycle will study. Number first. Number second. This is the number first of answer. Number second answer is that, see, during the Carnot cycle, you can measure the extent of irreversibility also. Like that, if you design the same temperature limit, and there is a, you have to efficiency of that one. The second solution, if you have efficiency of that one, now you can compare, and now you design the actual cycle. So the actual cycle is deviated from this Carnot cycle, so you can measure the extent of the deviation. Also, you can measure the extent of deviation so that you can apply that, improve that cycle and to approach the Carnot cycle. Okay, these are the methods. Okay, now so this is high. Now this is your cycle. This is your cycle. Okay. So this is your isothermal. This is your isothermal, high temperature. This is your low temperature. This is the cycle. Okay. Now there is a high temperature. Now in this condition, this is work in here. Okay. This is the compression, and there is a work out. Work out. There is a heat supply throughout. There is a heat supply throughout. There is a heat supply throughout. And there is a heat rejection throughout. So this is a heat addition QH, and there is a heat rejection QL. Okay, so this is your cycle. And good afternoon to you. So this is your cycle. Now you can achieve. So this is the reversible cycle. So what is the we know that the efficiency. What is the efficiency? We know that the efficiency. What is the efficiency of any engine, any device? Output, net output, net work net by heat supply, QH. Now, if you convert this first law of thermodynamics, this is 1 minus QL by QH. Okay. Now, according to absolute thermodynamics temperature scale, you can write like that: 1 minus TL by TH. So this efficiency is equal to 1 minus TL by TH. This efficiency is applicable only for the reversible cycle. Applicable for reversible cycle. Only for the reversible cycle. Okay, no problem at all. Now, there must be some important point which always remember. What is that? See, my dear. This is very, very important, I am telling you. What is that? See. What is the important point? Always note. The Carnot cycle, either input or output, if you design, the temperature limit is fixed. That means you cannot change the temperature range. And that cycle work between the high temperature and low temperature. Okay, this is first point. That means this is always remember, note. What is the first point? First point is that we have a cycle. That means we have a cycle with fluid. We have a cycle with fluid operates between two temperature limit. Two temperature limit. What is that? TH and TL. This is fixed. Okay. And does produce net work. Does produce net work. Does produce net work. So it is satisfied the Kelvin-Planck statement, right? The cycle operates between two temperature limit and produce a net work, that is the satisfied the Kelvin-Planck statement. Kelvin says that it is never construct a cycle which operate a single thermal reservoir. Okay, so this will satisfy the Kelvin-Planck statement. That means, so it satisfied the Kelvin-Planck statement. Correct? Correct? This is the first line. What is the second line? What is the second line? The second line is that in this cycle there are two reversible adiabatic process and two reversible isothermal process. Okay. Two reversible adiabatic process and two reversible isothermal process. See, my dear, what you will done in the reversible adiabatic process? In this process, their work will transfer. Yes or not? Work transfer. Okay. And during the isothermal, reversible isothermal, in that one, this is very important observation I am telling you. In that one, heat transfer. Heat transfer. In this cycle, there is a heat transfer. So, work transfer and heat transfer. Work transfer at reversible adiabatic process. So, my dear, this work transfer is a thermodynamic work transfer, network transfer, and this is your quasi-static process. It must be a quasi-static process. Quasi-equilibrium process. And we know that quasi-equilibrium process must be internal reversible process. Yes or not? Everyone? Yes or not? Now, this heat transfer must be a infinitely small temperature difference. A small temperature difference, that means delta T tends to 0. So, if heat transfer through infinitely small temperature difference, so it is external reversible. External reversible process. So, the cycle is internally reversible and external reversible process. That means this cycle is the total reversible. That means it is a reversible cycle. Okay, it is a reversible cycle. That means it is a reversible cycle. That means it is a reversible. Reversible, that means internally as well as externally. Okay, so this is the second note point. Now, what is the third note point? The third note point is that, what is the third note point? Carnot cycle is not a only reversible cycle. Okay. Carnot cycle is not a only reversible cycle. Only reversible cycle. It is a just example of a reversible cycle. Okay. In the world. In the world. Wait a minute, 1 second. Just remove this one, no problem. It is loose sense, no problem. Only reversible cycle. That means it is an example, right? That means, so it is just a, so it is just an example. An example of reversible cycle. This is the note number 3rd. This is also very important note. Okay. Note number 4. What is the note number 4? Note number 4 is there are a substance undergoing in the cycle. Now, the fluid which is flowing in the cycle is a control system. Yes or not? See, my dear, control mass system. See, there is no any mass enter or exit in all the process. During the cycle, the same fluid will be flow. During the cycle, the same fluid will be flow. That means this is a control mass system. That means a Carnot cycle, if you design any cycle with respect to a Carnot cycle, there must be a control mass system. There must be a control mass system. Okay. Right. So number 4, very important, I'm telling you. Okay, so Carnot cycle, so here the substance, that means here the fluid undergoing the cycle is under control mass system. Undergoing the cycle is under control mass system. Very important. That means control mass system, it is a control mass system, that is closed system. Okay, this is also very important, I am telling you. Okay, now note number this is note number 4. Now, what is the note number 5? That means the cycle is a closed system. Carnot cycle is a closed system. What is the note number 5? Carnot cycle is, and we have to, so it is sufficient. Okay, no problem. Now, we apply this cycle in a power producing cycle. Okay, so what is that, beta? We'll draw that one. What is that? Take a shape. So, one second. This is your boiler. Okay, this is your boiler. Right. So, from that, one second, beta. From that boiler, there must be a. So, first is what process, beta? Adiabatic compression. First is adiabatic compression. So, if you design the power plant, that means this power plant work on a heat engine. So, if you design a heat engine, that is heat engine, will the efficiency of other reversible cycle, okay, what is that? First question. Other example of reversible, yes, I will discuss, no problem. Next question, will the efficiency of other reversible cycle are same or different? Will the efficiency of other reversible cycle, yes, it is same, I will just discuss. It will same, but the condition is this one. Cycle of the fluid operating between the same temperature limit. That means this is the Carnot principle. What you are asking, that is the Carnot principle, and we will discuss. Okay, other example of reversible cycle, yes, that is a power plant. Rankine cycle, it is a reversible cycle. Okay, Otto cycle, reversible cycle. Diesel cycle works on a reversible cycle. Dual cycle works on a reversible cycle. So all the thermodynamic cycle what you design, except vapor compression. In that vapor compression, there is one process known as throttling, and throttling is a highly irreversible cycle. So all the reversibility is vanishes. If there is a cycle, n number of process, if any one of the process is irreversible, all the process are converted into irreversible cycle. So except vapor compression refrigeration cycle, all the cycle is behave as reversible cycle. Okay. Now. So, this is a boiler, heat engine, power plant. This is a heat engine, this is a boiler. This is a boiler, okay. In the boiler, heat will supply. So, in the boiler, beta, we supply the heat. From the external source, which have a high temperature, TH. Okay, which have a high temperature TH. Now, before that, the starting process is your adiabatic compression. So there is a, so if you design the heat engine on the power plant basis, the compression will done through a pump. If you design a pump, pump is always. So what is the difference between compressor and pump? There is a little bit difference. What is that, beta? If I will discuss you compression process. Compression. If you compress anything, okay, so compression will done through a compressor device and through a pump. This is very important, okay? This is very important. So compression of any fluid will done either with the help of compressor or either with the help of pump. The compressor, design of compressor is like that. This is your compressor. This is also open system. And the pump is like that. This is your pump, okay? This is eye of the pump, okay? Okay, this is your pump. Okay, this is our system and this is our system, okay? This is our system. This is your control volume. This is your control volume. And this is also a control volume. This is a fixed volume. This is also the fixed volume. Okay. What is that? Will efficiency of other reversible cycle are same or different? No. Okay, I will already explain. No problem. This is a control volume. This is also a control volume. Okay. So this is a pump. Now, the fluid is in here. Let's suppose this is a compressor. The fluid is in, and there is a compressor, which is fluid is out. Okay. Here is the fluid is in here, and fluid is out here. Mass flow rate in and mass flow rate exit. If it is a steady device, both are the same. Mass flow rate in, mass flow rate exit. Okay, this is a pump. In both the cases, we are supply the work from the surrounding. That means this is work input. In this case also work input. Okay, very important. If you draw the power, so W dot, there is a W dot. Okay. Now, what is that, beta? If you compress, obviously volume will decrease. If you compress, volume will decrease. But the decrement of the volume in the pump is very negligible, and decrement of the volume of the fluid in the compressor is very high. That means its possibility that it will handle gas or a superheated vapor. It will handle a gas or a superheated vapor. But this handle a fluid which is in the form of liquid. That means you are taking a pump water from the low reservoir and you deliver the high range. So this is your low pressure, this is your high pressure. Also this is your low pressure, this is a high pressure. Okay. So precisely, compressor, the volume change is very high. Very high. In the pump, the change in volume is approximately negligible. Okay. So it is handle gas. Okay. It is handle liquid. So beta, so the process, the both device, that is open system, the process, the approach is clear. It is a compression. That means low pressure P1 to reach a high pressure P2. This is clear. That means if you want the fluid which will reach at a low pressure to a high pressure, there must be a compression. And compression will done throughout a thermodynamics by the help of compressor or by the help of pump. Compressor will handle gas, pump will handle liquid. Okay. Now, during that compression, either by the pump or a compressor, this is a reversible adiabatic. Okay, understood? Already we'll discuss. This is a reversible adiabatic. What is the process? Reversible adiabatic. Okay, we'll discuss. That means the compression will done. So it is an ideal case. Okay, compression, it is ideal. It is not actual. There must be irreversibility. So we can calculate the isentropic efficiency. We'll discuss in that entropy chapter. So in this case, reversible plus adiabatic, that means internally, this is reversible, total reversible. Okay, this the reversibility is a total reversible. Okay, so there is a compression. The compression will done. So this is a low pressure, and this is a high pressure. So if you achieve a fluid from low pressure to high pressure, there must be a compression process. Okay, so in the power plant, that means which work on a steam cycle, that means NTPC, National Thermal Power Corporation Limited. NTPC, National Thermal Power Corporation Limited. NTPC, in the NTPC we have a boiler, and that boiler, in the boiler, this is a high pressure, and there is another device which will talk to you, have a low pressure. So what is the pump is function? The pump of function is to achieve successfully from that low pressure to high pressure. So this is your high pressure P2, and this is your low pressure P1. From where it is come and from where it is going, this is going in the boiler, and this is come from the condenser. So in the pump, this entry is to the condenser. We'll detail discuss in the power plant chapter. Okay, condenser, and where it is going, discharge in the boiler. Discharge which is in the boiler. So boiler, it is a high pressure, condenser, it is a low pressure, and it is not a low, it is a negative pressure. That means below the atmospheric pressure. Okay, in the condenser, below the atmospheric pressure, negative pressure is done. Okay, now it is used in a gas turbine. That means power will produce. That means you have produce the power. There is a steam power and there is a gas power. That is called gas turbine. This is called steam turbine. So steam turbine use a compressing process is due to the pump. Gas turbine use the compression is due to the compressor. Okay, gas turbine. And there is also a burning in the power plant. There is also in burning. A burning will take place in there is a combustion chamber. Okay, so we'll discuss in the detailed power plant. Okay, so that is the boiler where the heat will supply. Okay, now from in the boiler, this is a high pressure. Okay, P2 pressure is P2 is high. So how to achieve high pressure? Due to the pump. So there must be a pump is there. So there must be a pump is there. So there must be a pump is there. So this is your pump. Okay. So from that pump, this is your P2 pressure. That means discharge. Here it is discharge at the pressure P2, and here entry at a pressure P1. Okay. During that, there is no any phase change. There is approximately no phase change takes place. Okay. This is throughout the liquid. And that is a compressed liquid. Okay. Now, so in this case, it will go to the boiler at the same pressure, P2 pressure. Okay. Now it will come entry is to the condenser. So there is a condenser is there, okay. This is condenser. In this condenser there is a condensing coil, okay, in which the fluid is in, liquid is in, and a mass of flow is in. There is a, this is cooling water, this is hot water. There is a heat, like a heat exchanger, very important. Throughout a power plant, where is the heat will exchange? Approximately it is a constant pressure. Maximum, we'll discuss. Maximum in a maximum power plant, maximum power producing or power absorbing, maximum, not, it is not always. There is a constant pressure process. There is a constant. So during the condenser, the pressure will doesn't change. So what is the mass flow? So it is, we have like a heat exchanger. In the heat exchanger, the fluid is transferring the heat. What is the heat exchanger? See, my dear, what is the characteristic of the heat exchanger? There are two characteristics, very important. What is that? When the fluid is passing, two types of fluid, one is hot, other is cold. When hot and cold fluid passing in the heat exchanger, there must be a heat transfer. But that heat transfer will not take place outside, will not go to the outside. That means that device is an adiabatic device. That device is an adiabatic device. That means within the internally there is a heat transfer. So this is the internally. This is the internally heat will transfer. There is a internally heat will transfer, okay. So there is also mass is flowing inside the boiler. This all are the open system. So there is a cold fluid. There is a cold fluid. In this one there is a cold fluid. Cold fluid in, and there is a hot fluid. Hot fluid out. And then there may be a phase will change, okay. So in this there is an exit, and this is your condenser. This is your condenser through which heat will reject. And this rejection is from low temperature, okay, heat will reject. Now from the boiler, see, there is a compression, that means work in this case there is a work in, let's suppose W dot in to the pump, okay, heat supply. Now there is a work in, this is your adiabatic, reversible adiabatic. There is a isothermal heat addition. Okay, heat addition, QH. Now again there is a expansion. So the expansion will take place. Will take place. Very important, I'm telling you. Expansion will take place in the turbine, and that is very important. So expansion will take place in the turbine. So this is your turbine, and there is a turbine shaft. Okay, this is your turbine over which the expansion will take place. Okay, and that fluid will come into the condenser. Okay, all the detail we will discuss in the power plant, no problem. So there is a condenser. Why it is requirement, why this is requirement, all types of the questions we will discuss in the power plant chapter. Okay, first we model as a Carnot. Okay, first we model as a Carnot. Okay, now first we model as a Carnot. Okay, okay. Now my dear, see the beauty. So what is your process? This is the process, compression 1 to P1 to P2. So this is your inlet is 1, exit is 2, exit from the pump, this is 3, this is also 3, this is 4 at inlet, again there is a 1. So there is a cycle. This is your cycle. Okay, this is your cycle, and that cycle, the same fluid is coming. So this is the power plant, and power plant is an example of closed system. Power plant is an example of closed system. Many times in the interview they will ask you power plant. See, all the devices are open system, but we connect as a closed system. So Carnot cycle, what is the fulfillment? Why this cycle will follow the Carnot cycle? Number first. What is that? It work on a 2 temperature limit. Yes, it work on a 2 temperature limit. Yes, it work on a 2 temperature limit. Number first. Second, the work and produce a net work. That means there is a WT. There is a WT and there is a WP pump. So what is the network? What is the network? W net is equal to work done produced by the turbine minus work input to the pump. So this is your network will produce. So work on a 2 temperature limit and produce a network that satisfied the Kelvin-Planck statement. That satisfied the Kelvin-Planck statement. Okay, and this have a closed system, modeled as a closed system, and all the process are reversible. All the process are reversible. So it as a model as a Carnot cycle. Okay, it model as a Carnot cycle. So power plant, if you take this as a system, this is your closed cycle. It is not isolated. If you draw the boundary to include all the component of a power plant, it is not isolated. I am telling you, it is not isolated system. It is a closed system. Why not it is isolated system? Why? Because the condition of isolated system, no work transfer and no mass transfer. Yes, there is a no mass transfer, but there is a heat transfer, energy transfer takes place. So precisely, this is a closed system. Closed system. How to draw a block diagram? How to draw a block diagram? So you take all this component, and this is your heat engine. This is your heat engine. Take all that. That is a closed system. This is a closed system, and this system, this closed system, will extract a heat from where? From this source TH, supply QH, reject a heat QL, reject a heat, this is QL, reject a heat QL at a temperature TL. This is your cycle. So in this cycle, what is that? There is a boiler, there is a turbine, there is a condenser, and there is a pump. So this is your pump, boiler, turbine, condenser. So this is your net cycle. Okay. Now you can define also thermal efficiency for this one, all the things. So this model as a Carnot cycle. So this is your closed system. This is your modeled as a closed system. This is modeled as a closed system. Closed system. This modeled as a closed system. Okay. This is clear? This is clear? Okay? This is clear, beta? So in this cycle, what is that? Now, what is if you apply the first law of thermodynamics, so we know that, this is very important, we know that heat transfer is equal to delta U plus W. Now you integrate cyclic, that means this is cyclic process. So integrate cyclic, okay. Which one is 0? In this 3 component, which one is 0, please? Which one is 0, please? Reply in the chat box. Which one is 0? Which one is 0? Of course, internal energy. Why? Why? Because it is a property. So change in property through a cycle is always 0. So this component is 0. So cyclic integration of dq is equal to cyclic integration of del W. So this will follow the first law of thermodynamics, cyclic integration of dq, cyclic integration of dw. That's it. So the power plant is satisfied the first law and it satisfied the second law also, Kelvin-Planck statement also, okay. So this we can use as a model of a Carnot cycle. So this is called steam power plant. What is called? Steam power plant. Steam power plant. And steam power plant will use in NTPC, National Thermal Power Corporation. Okay, this will use in NTPC, steam power plant. So steam power plant is an example of reversible cycle. It is an example of reversible cycle. Clear? Everything is clear? Now, Atul, your question also clear? Okay. Now, if it is clear, we'll go through the next slide. What is that? Carnot principle. What is the Carnot principle? Carnot principle. This is the principle. Okay. Or Carnot theorem. You can sometime there is a Carnot theorem, sometime there is a Carnot principle. Don't go detail what is the principle, what is the theorem. We have no any interest. But what is the main funda? What is the main thing? Why this Carnot principle is so important? So beta, this is the proposition regarding the efficiency of Carnot cycle. Very important. What is this? We'll write here, no problem. We'll write here, very important, I'm telling you. No can we tell you like that one. Okay. So what is that? What is that? That means it is a propositions regarding efficiency of Carnot cycle. Efficiency of Carnot cycle, very important. It is the proposition regarding efficiency of Carnot cycle. That means it tells about the efficiency. What the first theorem till I don't go into detail that the proof is important also, not important also. Sir, what is your statement? The statement is that if you find the pure detailed analysis of the Carnot cycle, please visit the online classes, okay? Online classes, okay? So only we will discuss what is the Carnot principle. So there are first principle is that working between same temperature limit, working between same temperature limit, working between same temperature limit. That means what is the temperature limit? TH, high temperature, and TL. That means that cycle working on a same temperature limits, efficiency of efficiency of any reversible cycle, any reversible cycle is same, is same. Yeah, you can say that working between the same temperature limit, efficiency of, and you can say like also that efficiency of irreversible cycle, irreversible cycle is less than the efficiency of reversible cycle. Less than the efficiency of, less than the efficiency of corresponding efficiency of reversible cycle. You can write reversible cycle. What is that? What this tells that? What this tells that? See, what this tells that? Say, will the second statement is the second. The second question is the second statement. So if this is your thermal reservoir, TH. If this is your lower thermal reservoir, TL. Now, it operate, the cycle is a irreversible cycle. This cycle, let's suppose this cycle is irreversible cycle. It's take a heat, reject it, no problem. And on the same temperature limit, there is a reversible cycle. Okay, on the same temperature. This is the irreversible cycle and this is the reversible cycle. So first relation says that, first principle say that the efficiency of a reversible cycle is greater than the efficiency of irreversible cycle. This is very important. Okay, this is very important. Now, there have a different conclusion of this one. What is this? If this is our situation, that means if you compare any cycle, they must be have a same temperature limit. That means if you compare an irreversible cycle with a reversible cycle, same temperature. If you comparing many reversible cycle, same temperature limit. If you compare all the reversible cycle, same temperature limit. So this is the first. Now second one is that beta, what is the second one? Just see. What is the second one? Just see. Second corollary is say that the efficiency of all the reversible cycle are same. That means we just now you see that the efficiency of a reversible cycle must be greater than the efficiency of irreversible cycle. Now, the second says that if there are a temperature limit, two temperature limit, TH and this is your TL, two temperature limit, and this two temperature limit, all the cycle are, this is your reversible cycle 1, this is your reversible cycle 2, this is your reversible cycle 3. Let's suppose this is your reversible cycle 3. Okay, like that. So this corollary says that all the cycle have a same efficiency with the same temperature limit, then all the cycle are reversible cycle. That means the efficiency of reversible cycle 1 is equal to efficiency of reversible cycle 2 is equal to the efficiency of reversible cycle This statement, what it tells that? What it tells that, beta? What it tells that? That means, this is the important. This tells that, that means the reversible cycle only depend upon the two temperature limit. If the two temperature limit are same for all the cycles, reversible cycle, then the efficiency is same. That means it is independent of the working fluid. This is very important. It is independent of the working fluid. What is the working fluid operating in this cycle? Like, let's suppose there is a petrol cycle, there is a diesel cycle, and there is a gas cycle. Let's suppose in this there is a gas, in this there is a petrol, in this there is a diesel. So if that different fluid is there in all cycle, but all the different fluid in the all heat engine, but all the heat engine working on a reversible cycle with a same temperature limit, so its efficiency is same, though there is a working fluid are different. This is very important. This is very important. That means, okay. So efficiency, all the references are same, two temperature limit are the same. That means it is independent of the working fluid. Okay, this is very important. What is say that? Independent of the working fluid. Okay, no, not depend upon. What is the working fluid? It is there. Now, what is the third? What is the third one? What is the conclusion? What you expect for the third one? See, my dear, what is the third? This is little bit logic. If this is your temperature limit, this same temperature limit, let's suppose this is your TH and this is TL. Same temperature limit. This temperature limit and this temperature limit are same. And this, on this temperature limit, there are a different irreversible cycle. There are different irreversible cycle. There are different irreversible cycle. That means this is irreversible cycle 1. This is irreversible cycle 2. This is irreversible cycle 3. Different irreversible cycle. Okay. Different irreversible cycle. Okay. Different irreversible cycle. So all the irreversible cycle have a same temperature limit but different cycle, different irreversible cycle. So that different irreversible cycle have a different efficiency. That means in this case the efficiency of this irreversible cycle 1 is not equal to the efficiency of this irreversible cycle 2 is not equal to the efficiency of irreversible cycle 3. This is very important. Okay, what does mean that? That means there must be one efficiency is maximum. If x not equal to y, y not equal to z, then in that quantity there must be one quantity is maximum. So in this cycle, let's suppose, in this condition, let's suppose take efficiency of, let's suppose second is maximum. Okay. Let's take efficiency of second is maximum. And what is the efficiency of this efficiency? These are irreversible cycle. So all the irreversible cycle have a different efficiency. So there may be a chance that one cycle have a maximum efficiency, but that maximum efficiency is always minimum of this reversible cycle. This is very important. Though this is the maximum, but this maximum is also less than this reversible cycle. This is the beauty. This is the beauty. That means if irreversible cycle 1, 2, 3 is there, and that have a maximum efficiency, let's suppose, and that maximum efficiency also will minimum of this efficiency of reversible cycle, like that. It is clear? It is clear, everyone, please? It is clear? That means what you can say that, sir, if this is our a thermal reservoir TH, if this is our lower thermal reservoir TL, and let's suppose there is a different heat engine cycle. 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 Okay. These are the different heat engine. Okay. That means, let's suppose this is an irreversible cycle 1. This is a irreversible cycle 2. Okay, this is irreversible cycle 2. Let's suppose this is a reversible cycle 3. This is a reversible cycle 4. What is the conclusion combined? You can say that number first. You can say that number first, sir, efficiency of 3 is equal to efficiency of 4. Yes or not? Efficiency of 4, number first. You can say that. Okay. What is the second? Second, you say that, sir, efficiency of first is not equal to the efficiency of second. Yes or not? What is third says that? Let's suppose this is a maximum. Let's suppose this is a maximum. So, third, what is the third? This second is what? Irreversible. Okay. And that is the maximum. Okay. That is the maximum. That maximum is lower than the 1 or 4. Is less than the efficiency of 3 or efficiency of 4. This is your combined form. This is very important, I am telling you. This is very important, I am telling you. These are the observation. That is a Carnot principle. That is your Carnot principle. Okay. So this is your Carnot principle. Anywhere you have facing a problem, please ask me. Please ask me. Please ask me. Is there any problem? Please ask me. Okay. Now, now take another note. See beta, note number first. That means heat transfer QH by QL is equal to TH by TL. This is your applicable only for the reversible cycle. Only for reversible cycle. How? It will prove also. See, we know that how it will prove. Very simple. See, efficiency of any cycle is 1 minus QL by QR, QH. Right? If that cycle is a reversible cycle, if that cycle is a reversible cycle, so you can write like that 1 minus TL by TH, no problem. That is given by the absolute thermodynamics temperature scale. Okay. That means this equation is applicable for any cycle. Okay. That means this ratio is applicable in the form of efficiency. That means efficiency is equal to 1 minus QH by QL is applicable for any cycle. This is for any cycle. Okay. either reversible or irreversible. But if you write this one, that means you can write efficiency is equal to 1 minus TL by TH. This is only for reversible cycle. Only for reversible cycle. And that is the maximum efficiency. That efficiency, this efficiency is have a different name. What is that? This is called Carnot efficiency. Carnot efficiency, also called reversible cycle efficiency. Reversible cycle efficiency, also called maximum efficiency. It is clear? It is clear? All the names are possible. Carnot efficiency, reversible efficiency, maximum efficiency. And this is efficiency of any cycle, any type of cycle. This is the efficiency of any type of cycle. Number first. What is the number second? What is the number second observation? Number second observation is that, so this is okay. We'll take second observation, right, like that. Okay. Okay. So you can remove this one, no problem. Now you can remove this one. Okay. Now, what is the second thing? The second thing is that, what is the second thing? Second thing is that if we take a very important thing, this is the thermal efficiency, okay? These all are the thermal efficiency, okay? Thermal efficiency. So, thermal efficiency, right, beta? This thermal efficiency what is the range? This thermal efficiency is less than, equal to, or greater than. This have three limits. What is the less than? This thermal efficiency of any cycle, yeah, this thermal efficiency is the actual cycle. Let's suppose this thermal cycle is the actual cycle. What is the actual cycle? Reversible cycle. So then this thermal efficiency is a actual efficiency, okay? And what is the actual efficiency for which one? Irreversible cycle. Irreversible cycle. Precisely internally, no problem. So, this irreversible cycle efficiency is less than the thermal efficiency of reversible cycle. Yes or not? So, this is your reversible heat engine, okay? Condition of reversible heat engine, okay? Now, sorry, this is your irreversible. Sorry, I'm very sorry. This is irreversible, na? This is not reversible. This is irreversible. Why? Because if thermal efficiency, reversible thermal efficiency is greater than the actual efficiency, that is a irreversible heat engine, okay? So, irreversible heat engine. That means in irreversible heat engine, we already know, in irreversible heat engine, the thermal efficiency of a cycle is less than the thermal efficiency of a reversible cycle. Yes, this is the Carnot principle. Now, if the thermal efficiency is equal to the thermal efficiency of reversible cycle, then this is a reversible heat engine. Reversible heat engine. Okay? Reversible heat engine. That means this must be a reversible heat engine. Okay? This must be a reversible heat engine. Why? Because this efficiency is equal when this is a reversible heat engine. And when the actual cycle efficiency is greater than the reversible efficiency, not possible. Not. Yes, that means you cannot design a cycle, you cannot design a device, which have a efficiency higher than the Carnot cycle efficiency. Carnot cycle efficiency. Okay, that means this is the utility. That means what is the question asked already, Atul? Why this Carnot efficiency of cycle is so important? Due to that, this is very important. That means if you're comparing the efficiency during that means the cycle is possible or not. So how we will check that cycle is possible or not? Due to that comparing efficiency. If efficiency is less than the reversible efficiency, possible. If efficiency is equal to the reversible, it is also possible. But if the efficiency is greater than the reversible efficiency, not possible. Now, in the possible condition, there are two conditions. If the reversible efficiency is greater than the actual efficiency, that cycle is irreversible cycle. If the efficiency is equal to the reversible efficiency of the actual cycle, that cycle is a reversible cycle. Clear? It is clear, beta? It is clear now? Is there any problem? Please ask me. Is there any problem? Please ask me, beta. It is clear, everyone? So once it is clear, now we will end up here and go to the, you will wait for the next session and we'll try to solve the problem. Okay? Thank you. Bye-bye.